emitting, you can use the optical fiber to land the LED signal. You can also have this edge emitting. So basically, then you have to cut. So you start with a 3-inch wafer, but you cut into some piece by piece. Then light can emit from the edge. That's called edge emitting. Both of them are very, very popular structures. They have different advantages, but that's two basic structures. Also, a couple of things to remind you. If you want to make a light source like LED, then you need special type of material. The most common material is gallium arsenide. That gives you the wavelength somewhere between, say, 800 nanometer to 1 micron. And that's gallium arsenide based material. And you use a lot of gallium aluminide, arsenide, ingots, those type of things. Another thing, material is based on indium phosphide technology. Actually, you use this indium gallium arsenide phosphide. That will cover the wavelength range from 1.3 to 1.6 micron. So you don't need to remember those things. The idea is when you need different wavelengths of light, then you need to use different material, and different material will cover a certain range. There's no material will cover the whole the spectrum you want. Then we also have, if you think about LED is something that can emit light, and photodetector is something that can collect light. One is LED convert electrons and holes into photons, but this photodetector is to convert photons into electrons and holes. Then you generate this current. If you detect the current, then you can detect how much light intensity you have, right? So actually, if you compare the LED technology and the photodetector technology, they're really, really similar. One is forward biasing, and the other is reverse biasing. So can you tell me which one is forward biasing and which one is reverse biasing? Think about it. Well, think about LED is something you need to generate photons out of electrons and holes. So you need to inject. In order to inject, it has to be forward biased, right? You need the current to start to fall, to flow in the circuit. And you also have modulators. Modulator is something you turn on and off of light signal externally. Say light is in here, and that's constantly on. But you control one arm, and the other end it's on and off. Say you have 1010 here, you also get 1010 in the other end. So usually people use this so-called Mahazanda structure. They change the refractive index, right? When you change the refractive index, then the phase accumulates in this path, and the other path is different. Then you use interference. You can create this 1010 idea. Then we move to semiconductor lasers. I'm going to spend a little bit more on lasers because I think it's important. Also, it's a very, very fun project to learn. It's also my research group has a lot of active projects on lasers. So, first, what laser stands for? It's actually called light amplification by stimulated emission of radiation. And as I explained before, stimulated emission of radiation is a concept proposed by Einstein, actually in 1920s. And 2010 is actually the 50th year anniversary of the laser, the invention of laser. So the idea of stimulated emission is proposed by Einstein. Then the laser idea was proposed by Charles Tang. Actually, Charles Tang is a graduate from Photonics University here. It's not far away from us. He visited Clemson a couple of times. The first demonstration is by Ted Mayman from the Hughes Research Lab in Malibu. It's a solid state ruby-based laser. Ruby is just a crystal, aluminum oxide. later on people demonstrate gas laser, semiconductor laser, and room temperature hydrojunctioning laser. The hydrojunctioning idea is also a really, really brilliant idea. So I'm going to spend a couple of minutes to talk about the first invention of laser. My PhD advisor, Amir A, he actually witnessed the first invention of laser. At that time, it's a race in scientific community. Who can invent the first laser, right? The proposal is there, and they make a laser that's in microwave. They already made it, but it's not that useful. Then there's all those research labs at the time. At that time, industry research is really number one. So they have GE Research Lab, they have IBM, also those labs in Japan. They all try to make the first laser because it's something remarkable. And this guy, Ted Neyman, he's the only one. He's the first one. So what's his key to be successful? Because 99% was working on CW laser. He is the only one working on the pulse laser. So why he wins? Because in earlier days, if you work on the pulse laser, because the total energy you have is constant. If you work in the pulse regime, that means you can get high power. When you get high power, then you can overcome the loss. So that's the lesson we should all learn when 99% people working on something constant, then you maybe think about some from a different perspective. Another thing is about the heat. When you work in the pulse regime, you don't generate much heat as you do in the CW domain. So that's the two key for him to be the first one that goes with the laser. And so that's also a lesson well learned. Let's see. Well, if you talk about laser, then the first thing you also need to understand a little bit about optical waveguides. Waveguides, you have the core and the cladding. You can use a ray picture to understand the waveguides. Like light is bouncing inside this core. All you need is to make the core is index large in the cladding. But the key is the core dimension should be similar to the wavelengths. If it's much, much bigger, then you don't have the waveguide concept. You can just use the ray optics because it becomes uniform. So if you look at the waveguide equation, so really, you have to introduce this optical mode concept is to solve the Maxwell equation with a certain boundary condition. And you have to introduce this concept of beta. So basically you say there is a particular profile, the light distribution inside this N1 and N2 medium, and it propagates in the z direction with a particular constant called beta. So all you need to do is solve the Maxwell equation. We're not going to into the detail of this optical waveguides. But the end result, you're going to have waveguide look like this, this, and this. We have one bump, two bumps, and three bumps. And each of them will have different propagation speed. There's different modes of this waveguide. If you use a ray optics picture, it looks like one is like this, another is look like this, the second one is look like that. So you can see the propagation, just the projection on the z-axis is different. So that means the beta is different. But they can all be totally, just experience total inter-reflection on this interface. So they're all guided modes. So that's the optical mode idea. This is a ray optics picture. At some point, if you study optics of photonics, you have to use the mode idea. And so-called laser is you have optical waveguides you put to a mirror. So that's something called resonator. If you have light inside, you can trap light, right? Because light will be just reflected, bouncing back and forth between that two mirror. And if you say that red region is active region, where you can provide some gain, then you can overcome loss. That's basically the idea to create a laser. You need the optical waveguides. You have two mirrors that provide the feedback and the gain to provide some mechanism to overcome the loss. So if you go to grad school, some professor apply, sometimes professor will ask, oh, you have taken electronics class, so tell me how laser works. You need to tell him that how laser works. You need a laser resonator to provide feedback. You need some material to provide the gain. Then later on, for that kind of laser, you have all different kind of optical modes inside. If you have some frequency selection mechanism like a grating, then you can create so-called single mode laser. So in this type of so-called DFB laser, you don't have mirror anymore. The grating will provide optical feedback. Think about the mirror, it's just reflected. It can reflect all wavelengths, all kinds of wavelengths will be reflected by the mirror. That means all kinds of wavelengths will get feedback from the cavity. But for DFB laser, it will only provide feedback for particular wavelengths. That's how you have a single frequency or single mode laser. So this thing is important because that's something you need use for the telecom. It provides high-speed telecommunication, and that's why in late 90s, probably you heard it. The telecom bubble is all about those things. DFB lasers, those OEIC chips. Some people made a fortune, but they collapsed in 3 years, right? And also you have some, that's a refractive index guide laser. You start with waveguides. So, but because laser can provide, all those gain material we find, they can provide extremely high gain. Sometimes you even don't need a waveguides. So like a gas laser, you don't have a waveguides there. You can still make it lace. We're not going into any this mathematics stuff. So if you have a laser, so especially it's electrical and pump laser, so what's the most important specs of this laser? So basically you need to look at ROI curve. You look at when you inject current, how much power you can get out of that laser, right? We're talking about electrical and pump semiconductor laser. You have the spectrum. So basically at the current injection, what kind of wavelengths of light will emit, right? So that's a spectrum. You have the near field. So basically imaging the emitting facet of the laser field. This is usually a typical near field of the laser. But apparently you have those multiple lobes, that's a multiple lobe laser. You also have far field looking at the laser. You put a camera far away. So the far field is like, if you're far away from a laser, if you look at a circular plane, look at how the intensity is distributed. So let's say if you take the sunlight, it will emit in all directions. Your light bulb it will also emit into all directions. What makes laser special is that it will only emit in a particular direction. In this, it will in a direction like this. Sometimes we make it really, really narrow angle. It will just emit in like a very, very small cone. So that's why you can get really high intensity even far away. Right? You can put a laser light even shoot on the moon, get it reflected, and you still get detected. That's because it doesn't even diffract like light bulb. Light bulb is something that will diffract into all directions. Then if it's really, really far away, then the intensity you get in a small area is really small. But the laser, if you think it's more like a beam, it will just stay together inside of the beam. Right? So if you watch the Star Wars, then they have this laser sword thing. Do you think that's possible? Yes, well, let's look at the scientific point of view. Is it possible? I mean, it's possible, but there's a really big error there. It will never be just this long, right? If you really make a laser sword, it will really, really long.
Yeah.
So that's a wrong thing. If they can make it's infinitely long laser sword, that's scientifically correct. Actually, now the Department of Defense they are trying really hard to make this laser weapon, to use intense laser to shoot a missile or even a vessel or a small plane. That's something possible. I mean, that's a laser sword, and the range is really, really long, right? But the problem is the size. In order to really cut steel, the size of laser is huge. There's no way you can make hand shell equipment. So, but maybe someday we'll see that. If you can, store extremely high energy in a small volume, then maybe you can convert that into light signal. Then it's possible. But again, if you make a laser shot, it shouldn't be this long. So if we look at let's talk a little bit about the semiconductor laser. So it looks something like this. It's a piece of 3-5 material. You have different layers. That's usually a different kind of material. Then you guide light in a small region, usually by creating an index difference. And this so-called active region, it's not something particularly special. It's just for all those layers, they have different band gap. So-called active region, it is the refractive index is highest and the band gap is lowest. So that way you can trap electrons and holes inside that region. So originally the idea is people just have a p-n junction. We have electrons and holes and we combine in the junction, right? But later on people find that idea will never work because the efficiency is so low, electron will pass by, hole will pass by. Then they'll say, okay, is there some way we can trap electrons and holes? So that's the whole idea of hydrogen. That's the idea when you had the Nobel Prize 30 years ago. So it seems so natural. So naturally nowadays, okay, you have electron and holes, we combine, get light, but now the efficiency is low, and then somehow we just trap it, right? Then they invent hydrogen thing. But if you don't know it, then it's something out of box thinking. So those are really smart people, but still take them 10 years to figure out this idea to have a hydrogen instead of homo junction. So that's the first picture we saw people use refractive index to control laser. But you can also use all kinds of periodic structures to control laser. You have DFB laser basically has a grating, provide the feedback in the longitudinal direction. You have the weak cell use grating to provide feedback in the vertical direction. You have photonic crystal, that's a 2-dimensional feedback. So in my research group, we also use periodic structures to control laser properties. So the main idea is usually for a piece of semiconductor laser, in order to have really good beam quality, the laser size is really small. But when it's really small, then the power is limited, right? Because when you increase the power level, the power intensity gets high. At some point, you will even melt the crystal. So in order to get higher power, you have to expand the size. But when you expand the size, the beam quality cannot be sustained. So that's a long-standing problem. People have been working on it for like the last 10 years. But we use something different using periodic structures. Use gratings, 2D gratings, and even cross gratings to control that. So that's some research we're doing in my research group. The basic idea is to use grating instead of index difference to control as a waveguide. So I'm not going into the detail. So basically, just kind of give you an idea what we do. So first we have this series, and we do some simulation to verify our idea. Then we, using the modern fabrication technology to make it and see if it really works. So we buy those materials from the vendor, then we make patent on it. So all those steps is kind of standard modern fabrication technology. You have EV writing, you have some etching. So if you like working with machines, then it's something you will enjoy working in the clean room. It's a similar process. Say Intel, they make those CPUs. It's the same thing. You do some capacitizing, beam writing, and create different structures and metallization. So this is some picture you take during this process. If you look at the feature size, the dimension is usually on the order of a couple of less than 1 micron, a couple hundred nanometers. Because think about this way, the light wavelengths we want to control is 1.5 or 1 micron. Then the structure you leave should be smaller, at least on the same order of size dimension of that thing, right? So in order to play with 1 micron light, you need structure smaller than 1 micron. That's kind of makes sense, right? If you have a 10 micron thing, you wouldn't be able to play with 1 micron light. So those are some kind of devices we're making. It's mounted on a chip. When we do the testing, say that's something I mentioned before, the Li curve. That's the near field, the far field. Indeed, we can get really broad laser emitting in a kind of this dimension. That's because you think about laser. It's a rectangular box. The emitting area is a rectangular box. In one dimension, it's really long. In another dimension, it's very, very short. So it's a rectangular box like this. But if you look at the far field, due to the diffraction, that in this direction it's really small, so it's going to be like this. In this direction, it's really long, so it's really small. So it's kind of a reverse image of near field. And later on, we make those 2D structures. And if you look at those like small posts, it's only about 300 nanometers big, and we have this nano post.